Okay, so we're now recording. This is the special office hours on Monday, October 26th. And the first question was to go over number 6A from the fall 2019 exam for test number 2. So here you have a really funky equation, y equals the parentheses 3x squared plus 3 times the inverse tan of x. Obviously, we've never done the derivative inverse tan of x. We will do that probably in the next unit. But you are told what it is, right? So if I tell you what it is, then you should be able to work it out. All you do is do your product rule. So think of this as u and think of this as v. Remember, the derivative for product rule is u prime v plus u v prime. So u prime is easy. That's just 6x. And leave it multiplied to the other part kept intact plus u kept intact, 3x squared plus 3 times derivative inverse tan, which is that. And that is your final answer. There's nothing you can really do to simplify that, even though you are told to simplify whenever possible. Personally, I probably won't say to simplify because I don't want you guys to get caught up in that. So yeah, that's it.
But how do we know v prime is equal to 1 over 1 plus x squared?
I told it to you. I'm not expecting you to know that. It's given to you. You just have to use it. The whole purpose of this problem is for you to utilize product rule and to not get caught up in what the individual derivative is. It's really more, can you go through the process of product rule? That's all I cared about in this problem. So that's something I could ask. Okay, and then there's another question that just came in the chat. For instance, can we say y or f of x prime instead of dy dx, or do you want us to use notation? I don't really care what notation you use. You can use y prime or dy dx. Doesn't really matter to me. Yeah, I'm not going to care too much. I mean, make sure you know what it means, right? That's what matters. So, Nico, anything's fine. Doesn't matter. Okay. So then a question came in about number 8 of the board problems. Let me put that up because there was a actually a mistake I made as well. Not a big mistake. Let me pull up the solution key for that one. Okay, let me clear my screen here. So going all the way down for number 8, part B, and I think that's what the question was about. Let me check the chat one more time. Yeah, let's just go over that. Okay. So first off, for number 8, the question was this. Let me pull up the question in case you guys forgot. So you had a piecewise function. Yeah, explain why it was not differential x equals 4. That's because it's not continuous at x equals 4. Remember, for continuity, 3 things must happen. The point must exist at that x value, which it does. You know, f of 4 is defined over here. So f of 4 does exist. But then also you need the limit as x approaches 4 of fx to exist. And it does not. So that's a check mark, but that's no. That's because the left-hand limit must equal the right-hand limit, which it won't. And you can check that out by just plugging 4 into 2x and 4 into x squared, and of course those are not the same. And remember, when you're not differentiable, you're not when you're not continuous, you're not differentiable. Therefore, you're done with part A. Now for part B, you have to find left and right-hand derivatives using the limit definition for one-sided derivatives. Now the question that was presented in the chat, and someone else asked us in email, is that, you know, if you take the derivative of this, I know that's 2. If you take the derivative of that, I know it's 2x. And of course, if I plug 4 in here, I get 8. And of course, that's 2. The thing is that when you're doing the formal definition of derivative, I mean, yes, the shortcut rules could be a little misleading, I suppose. But if you have 4, 1, 2, 3, 4, and that's yikes, all the way up here at close to 8. It's gonna be kind of like this, I suppose. Then you have a parabola starting at 4, but it's at 16. It kind of does that, right? So when you try doing the left-hand derivative, you're taking a point close to 4. Remember, that's gonna be like 4 plus 4 plus h, and that's gonna be 4 right there. You're gonna be getting a slope that's pretty much infinite. We try working that out. And so if I show you the solution key, so when you do f of 4, remember it was defined, x equals 4 was defined for x squared, not 2x. So you had to plug in 16 into here, just like we did over here for the right-hand derivative. So when you work this out, you get some really funky like this, which can be reduced like that. And if you're plugging something close to 0, this would be essentially, and remember, you're coming 0 from the left, so that's the one mistake I made. So essentially that's gonna be like infinite plus 2. And that's what we kind of saw, that really steep slope when we're trying to find left-hand derivative. So it's really D&E for that. It's not gonna be, 2 that some people might think it is. So, but don't worry about that. I'm not gonna really be asking that. I think I'll probably just ask something else about the difference between continuity, like maybe some true-false questions about the logic behind that connection, as well as like maybe solving for constants. Like we had this problem here, you guys might remember from the homework. Let me go to homework images. Number 11, I think. No, it was number 12. Oh, come on, homework images. Number 12. Yeah, I'll be asking something kind of like that in the realm of continuity and differentiability. So I think we tackled that one. Then someone asked in the chat, I think Zoe, this is your question. Hold on. Can you go over part B of number 14? And why do you use different French for limit definition finding left-hand derivative? Let me see what you mean by that, because I'm not 100% sure what you mean by that.
Mr. Almashny, sorry, I have a follow-up on the last question.
Wait, go ahead. Yeah, please.
So how do you know when you're supposed to use the shortcut to the derivative versus using the entire equation?
Well, if I ask you to, because I asked you to use the limit definition. If I don't ask you to, then use a shortcut. The shortcut will be helpful, like for example, for this one right here, for number 39. And maybe I'll put that as a hint too, to tell you to use a shortcut. I'll tell you, don't worry. Like here, I think using a shortcut would make sense, right? Because it's just be too much work otherwise. Like here, the shortcut is of course -1 for the derivative. Here it's gonna be a times 2x plus b. So I think the shortcut would make sense here. I'll tell you, so that's how you can tell. And if I don't tell you, then assume shortcut. So there we go. But then, well, before I get to number 14, that's Zoe's question. Hadley put, if limits D&E, do we have to indicate which infinity is approaching? You do if I'm asking you to classify why it's not differentiable. Like if I ask to, like if it's a cusp, right? Or if it's a vertical tangent, then you would need to know that. And a lot of times you could just be able to tell from the graph and just give a graphical explanation, and that'd be fine. But other than that, if it's just like, hey, just, you know, the limit does not exist, that's fine too if I'm not really asking for anything very specific. And Nico put a question for our answers. Yeah, I already took your question, Nico, sorry. Yeah, I don't care where you y prime, f prime, dy dx. I mean, whatever the question uses, you don't have to use that notation, just make sure you know what it means. Another question was just posted, I need help talking about the difference between corners and cusps, graphing algebraically. I'll do that when I go over, I think, from the old tests from last year. I think number 14 gets into that stuff. Let me pull it up right now. Yep, actually not quite. That was number 13. But I will tackle your question about the difference between corners and cusps in just a minute. But questions about number 14. And again, what was the question again? Hold on. Oh, Jesus, chat session's being weird. Part B of 14, why do you use two different functions for limit definition of finding the left-hand derivative? Okay, so that's a bonus point. Let's see, let me read the question first because I have to reacquaint myself with it. So you have piecewise function 8x and x squared. You wonder if it's differentiable there. Obviously, if you do the left and right-hand derivatives or the shortcut rules for them, you get that. Yeah, the problem is that obviously for part A, it's not differentiable because it's not continuous, right? If you were doing the left-hand limit, you would get 32. The right-hand limit, you get 16. We plug 4 straight up in each expression. So that's the answer for part A. Conceptually, Blake is incorrect because you don't have continuity. You need continuity to be differentiable. So that's part A. Then for part B, now look at the answer key because let me see what was going on there because I'm a little bit confused with the question that Zoe's posting. Let's see here. So let me look at that question one more time. The question is, why do you use two different functions for limit definition of finding? Well, oh, okay. Now I understand your question. Okay, I understand now. Here's the thing. When you're doing, I'll just keep on the solution key. That's probably easier. When you're doing this, of course, we use that one, right? When you're doing this, we're using that one. Now remember, this is f of 4. X equals 4 is defined for x squared, not for 8x. 8x is just x is less than 4 straight up. X greater than or equal to 4 is for x squared. So you got to use x squared for f of 4. Now for f of 4 plus h, remember it's a left-hand derivative. H is negative. It's a little bit less than 0. So when you're doing 4 plus h, you're doing 4 plus a negative number. That's definitely going to be less than 4. That's why you have to use that one. So now you plug 4 plus h into 8x. You work that out. And when you get that, you're going to get something very strange, 16h plus 16 over h plus 8, which is basically negative infinity. Now, it is strange with the shortcut rule. The shortcut rule, you do get 8, right? So if I tell you these a limit definition, then do that. So that's how you can tell. I'm not going to just vaguely say, oh, find me the left-hand derivative for this piecewise function. And you're torn, like, oh, do I do the shortcut rule or do the limit definition? I'll tell you which one to use. But going back to Zoe's question, the reason why we use x squared is because f of 4, it's defined x equals 4 for x squared. X is greater than or equal to 4. F of 4 plus h was a little less than 0 because this h is going 0 minus, right? H is a small negative number. 4 plus small negative number is less than 4, so you got to use 8x for that one. And technically, the limit definition is the right way to do the left-hand derivative because that's truly what's happening. The shortcut rule, again, is a little bit deceiving here. So it's helpful for a problem like I just showed you over here. When you're trying to force differentiability, we're trying to force the issue, then yes, please use the shortcut rule because that's going to be easier. Whereas we knew we're not differentiable, number 14b of the test from last year. So next question was, understand the between corners and cusps, graphing algebraically. Let me have that quick discussion, and then I want to do number 13 from a test from last year. Because that one's a little strange, but it's a very good problem. And I'll ask something like that on the test tomorrow. because I like that question a lot. So free response, there'll be a few more free response than last time, and fewer multiple choice. Before I tackle 13, let's have a little bit of a conceptual discussion about corners, cusps, vertical tangents, all that stuff. So let me share a whiteboard. Okay. So say I got a piecewise function like this. So I have like 2x and negative x plus 1. And this is true at, actually, let me redo that. Give me one sec. Negative x plus 6. This will be true when x is greater than or equal to 2. This will be true when x is less than 2. So if I were to graph that, obviously if I put in 2 into 2x, I get 4. It's included, slope of 2. So you go up 2 over 1. Boom, there you go, right? Negative x plus 6. So then x is less than 2. So if I plug in 1, for example, I get 5. And y-intercept is 6, and it's a slope of negative 1. Excuse me, that's kind of bad. It should look kind of like this. And there's a hole there, but the hole gets filled in by the filled-in circle at for x equals 2 at x for 2x. So that's clearly a corner visually. Algebraically or analytically, what's happening if I take the derivative? That's going to be 2, and that's going to be negative 1, right? So clearly, my left-hand derivative at x equals 2 does not equal my right-hand derivative at x equals 2. And in this case, I was able to use my shortcut rules because I was continuous. So I'm not going to have anything weird kind of happening with the previous problem that we did. Because when you have those discontinuities, when you get that really inconsistent answer between the or the discrepancy between the shortcut rule and the limit definition. But for continuity, shortcut rule is fine, but they're different, of course, right? So your left-hand derivative is not equal to your right-hand derivative, and they're also finite values, right? Now for a cusp, same thing, left and right-hand derivative won't equal each other, but they're going to be infinite values. I'm going to show you that in just a sec. There's a question in the chat. Okay, that's another kind of question. I thought it was about this. Yeah, I will go over 39B from homework number 12, no problem. So yeah, that's a corner, right? Now for a cusp, what's going to happen, like y equals x to the 2/5 power, we talked about how to graph power functions. So in the first quadrant, when that's between 0 and 1, it looks like this. And that's like saying the 5th root of x squared. So I can plug in negative numbers, of course, but stays positive because squaring a negative. So you get that. So that's graphically what's happening. And then if you draw tangent lines close to x equals 0, you can see as it closer and closer to x equals 0 from the left side, that's a negative slope. From the right side, it's a positive slope, right? So the left and right-hand derivatives don't equal each other at x equals 0. What's happening is that this is negative infinity, that's positive infinity. Or if you reversed it, like let's say like y equals negative x to the 2/5 power, which would be flipped over, then of course it'd be reversed. The left-hand derivative would be positive infinity, and the right-hand derivative would be negative infinity. So that's going to give rise to a cusp when it happens. So that's why we're lacking differential. But now if you did a shortcut rule, which you guys should know now, derivative gives me 2/5 times x to negative 3/5, right? or it's going to be 2/5 times 1 over the 5th root of x cubed. Well, you can't plug 0 into that. So that's why another reason why you're not differentiable with x equals 0. That would be undefined. So that's another way you can kind of look at it too. So that gives rise to a cusp. Vertical tangent will happen when you have something that looks like this. Y equals cube root of x is a great example there. So what happens graphically, the left-hand derivative and right-hand derivatives are both approaching the same thing, but it's both positive infinity. And that's kind of an abstract idea. What is infinity, right? I don't know what that number is. Hence, I don't know what the slope of the tangent line is. That's why it's not defined for differentiability there. Or it could be reversed. Kind of like that, where that would be the negative cube root of x, right? That could happen too. In this case, both left and right derivatives are negative infinity. If you were to actually do a shortcut rule for that, you have 1/3 times x to negative 2/3. That's 1/3 times 1 over the cube root of x squared. You can't plug 0 into that. That'd be an issue. That'd be undefined. So that's why it's not differential x equals 0. So the question is, new question about this stuff. So left-hand derivative, different parts of a piecewise function. So to answer your question, Rosemary, let me go over number 39 from homework 12. I think that might clear it up a little bit, why we want to match it up. So let's do that. So Lizzie asked about 39B of homework 12. So that might clear some things up. And then I'm going to talk about 13 from the old test, because that's a good one. So let me clear this up. And again, this is being recorded. Let me go back to sharing a full screen now. Hold on. Share full screen. There we go. Okay, let's go over this problem. So this is a piecewise function, of course, and you're asked how does A and B have to be related for this to be continuous? Well, to be continuous, you need 3 things to happen. And for all x, well, where is this gonna have a problem? There, right? It's not gonna have a problem anywhere else because 3 minus x is linear in nature. That's gonna be continuous everywhere as long as you have, a domain of all real numbers for it. The second part's quadratic. That's gonna be fine, but it's a piecewise nature that makes this an issue, and that issue is gonna happen. An issue with continuity or differentiation that could happen at x equals 1. So let's actually take the derivative here. Actually, before I do that, sorry, I'm getting ahead of myself. Continuity, right? Let's focus on continuity. So firstly, you need f of 1 to exist. Well, of course it exists. You're told that this is defined for x greater than or equal to 1. And what is f of 1? That's just going to be a plus b, because you plug 1 in for x. Now, you want to make this differentiable as well. And by the way, before I get too carried away, remember also that you need the left-hand limit to equal the right-hand limit, because that's your second condition, right? Our second condition is that the limit as x approaches 1 f x has to exist. So you need the left-hand limit to equal the right-hand limit. So you need 3 minus x to equal ax squared plus bx. Well, if you plug in 1 for x, you get a plus b equals 2. And we know that f of 1 equals a plus b, so that means that f of 1 has to equal 2. Because that's the third condition. F of 1 has to equal those x approaches 1 of f of x. And we know that f1 is a plus b, and the left-hand limit's 2, and the right-hand limit's a plus b, so we have to force that issue. A plus b has to equal 2. So that's part A. For part B, and the shortcut, by the way, for A, just set them equal to each other and plug 1 for x. Set 3 minus x equal to ax squared plus bx, plug 1 for x. You'll get a plus b equals 2. That's the relationship for part A. Now for part B, we have to take it a step further now. We have to force differentiability. So you could use a shortcut rule. That's going to be -1, and that's going to be 2ax plus b. Remember, derivative of x squared is 2x, but there's an a next to it. Derivative of x is 1, but there's a b next to it. And of course, for these conditions here. And I dropped the equal sign because we're not 100% sure if this will be differentiable yet, so we have to force it to be differentiable. So then, in order for this to be differentiable, you need the left-hand derivative equal the right-hand derivative for differentiability. So -1 equals 2ax plus b, and you're forcing set x equals 1. So -1 equals 2a plus b. So now you got two equations of two variables. Let me highlight the two equations in yellow. You got this equation, and you got this equation. Now you should use systems of equations, which you guys should be comfortable doing. You guys have done that many times throughout your last 5-6 years of school, in Algebra 1, pre-algebra, and Algebra 2, and pre-calculus, just in geometry even, we keep reinforcing it. So you should be able to solve that just fine. You get -3 and 5. So that's how you would do a problem like that. I'll ask something like this on our test because I like this problem a lot. And looking at the chat again, hopefully that kind of clears up the confusion about left and right hand limits. So for left and right hand limits, you need it to have them be the same. So you set both parts of the piecewise function equal to each other and plug in whatever number you see for the inequality, in this case 1 for x. That's for continuity. And then for differentiability, you need the left and right hand derivatives. So you got to take the derivative of each expression, set them equal to each other, and plug in whatever x value is going on here, 1 in this case, and you got to have both those sides be equal for the differentiability part. So hopefully that clears that up there. Okay. So great questions. We've covered a lot of ground thus far. Let me go over number 13 from the test from last year, because that kind of ties in with everything we've talked about so far, and then see if there are other questions that come up. Because I think that's a good one to ask. So let's look at test from last year, number 13. So you're told that you have a function f. It's got to be continuous and has the following properties. The domain's all real numbers. F has exactly 2 zeros. It means you have 2 x-intercepts. It's differential everywhere but those 3 points. So it means that at these 3 points, there's a few things that could happen. You could have a discontinuity. You could have a corner. You could have a cusp. Or you could have a vertical tangent. So we're going to have to keep our eyes open for any of those 4 possibilities for each of those 3 points. Here, these are just points straight up. That's easy, right? -5, -4. 3, -2. 5, 1. So I'm actually going to check that off right now. -5, -4. 3, -2. And 5, 1. Congratulations, you're getting some points for this problem now. The rest looks a little funky, and this is the calculus. So this requires calculus knowledge. So how do I use calculus knowledge here? Well, let's look at what's happening at this part right here. Now, the whole embodiment of that, the limit as h approaches 0 of all that big chunk of f of -5 plus h minus f of -5 over h, that's a derivative. So this right here is actually a left-hand derivative because you have a little minus right there. Whereas this is a right-hand derivative because you have a little plus right there. And you told the left-hand derivative, and these are both at x equals -5. Because you got -5 inside here, inside the function. So you're told the left-hand derivative is -infinity. The right-hand derivative is positive infinity. Which of these 4 is that going to be? Anyone can speak in the microphone or type in the chat.
Cusp.
Yep, cusp. Yep. It's a cusp. So it's -infinity to the left. So I'm going to do this. and positive infinity to the right. So I'm going to do something kind of like this. Now, I could have drawn my cusp like this, or I could have drawn my cusp like this. I mean, the bottom line is the left side's got to be negative infinity, the right side's got to be positive infinity. But why did I draw it more like this and kind of just left that open-ended? There's another thing going on here. Go ahead, Son.
That's a vertical asymptote.
Horizontal asymptote, actually. I think that's what you meant. There's a horizontal asymptote. Where the heck is it? Right here. X approaching infinity. We've talked about this in the previous unit. So everything that we've done in the previous unit still applies, right? Gets reinforced here. And you're told that that limit as x approaching infinity is going to be -1. So it's going towards -1. So I'm going to draw a little dash here. Now, do horizontal limits have to be the same on both sides? Absolutely not. You can have two different horizontal limits. You can do whatever you want. It's a piecewise function, right? Or at least that's what we're trying to do here. So, yeah, I mean, you don't need to have the end behavior to be the same on both left and right ends. Absolutely not. So I've checked this off, and I've checked this off. Now, let's look at right below. You have x approaching 3 from the left is going to be 1, but f of 3 is -2. So f of 3 does not equal the limit as x approaches 3 from the left side. So it's definitely discontinuity. So definitely have discontinuity x equals 3. But they did it a left-hand derivative, so the left-hand derivative doesn't equal, or so the left-hand derivative is 1. So it means, sorry, the left-hand limit. Sorry, the left-hand, sorry about having confused, guys. The left-hand, this is a left-hand limit. It's not a derivative, it's just a left-hand limit. That's approaching 1 when you're approaching 3 from the left. So what I'm going to do is draw a little hole here and do that. So as I'm getting closer to 3 from the left, y is getting closer to 1. But f of 3 is -2. And you're told to make this as continuous as possible. Of course, it's not continuous there, given what, that f of 3 doesn't equal the limit. So we know there's going to be a jump discontinuity there. So here we have a jump.
Mr. E,
Yep, go ahead.
if you were not told what f of 3 is, then would you fill in the circle at?
You can, because these are open-ended problems, mind you, right? You could. I'll
Okay.
probably try to make it as less open as I can to avoid the confusion. Okay, so I'm probably going to connect these two now. But what's going on over here? What's happening here is that that's another derivative. So you have to be able to recognize the derivative expression. That's a limit definition of derivative. That's again a left-hand derivative and a right-hand derivative, both at x equals 5. And both are going towards positive infinity. So which of these four it's going to be? Is that a discontinuity? Is that a corner? Is that a cusp? Or is it a vertical tangent? What's going on at x equals 5? And anyone can chime in. It's vertical tangent. Thank you, Nico. So I'm going to draw a vertical tangent there. Let's go back to red. So that's checked off. And then finally, this is end behavior. On the right side, if I'm going forever to the right, so there's no horizontal asymptote on the right side. Whereas that horizontal asymptote on the left side when x approaching -infinity. So that's why it's going up forever. And that is your graph. So this is something I'm going to have as a free response question. It's a good problem. It really kind of forces you to understand everything we've done thus far. So, yeah. Any questions about this one, or if there's other things you guys want to talk about?
I have another question.
Yeah, go ahead, please.
For the limits that gave us the vertical tangent, would they have been equal to negative infinity? And if yes, would that have looked the same, or would it look different?
Ooh, that's a good question. I should ask that tomorrow. No, I'm just kidding. No, I actually think it's impossible. Because I think given the way this is situated, because what I told you where f of 5 was, I don't think I could have done it as a negative infinity. Because I could have probably done this. I could have moved x, if x equals 5 could have been down here somewhere, and I could have done that, right? But then you have this also, that makes it kind of inconsistent. But going back to how it was before, yeah, I don't think I could have made that negative infinity for left and right hand derivatives at x equals 5, given the way, I mean, the only other thing I could probably think of, it would have been just so bizarre. I guess I could have done like this, but then on the right side, it's going forever towards positive infinity, when x is going towards infinity. So I guess I could have done, that's just too weird. So I won't do anything like that, but good question though. Okay, so another question in the chat. Number 9 test. Okay, good. Let's keep moving here. Let me clear my screen. Oh yeah, that's a good one. Okay, so this is kind of like number 39 from homework 12 that I went over just a few minutes ago. So you want this to be continuous at x equals 2. So then this also has to happen. You need f of 2 to exist, which of course it will, because it's right there. You also need the limit as x approaches 2 of f of x to exist, meaning that you need the left-hand limit to equal the right-hand limit. The left-hand limit is just going to be p times 1 squared plus 1. The right-hand limit is just going to be q times 2 minus 5. If you clean it up just a tad, p plus 1 equals 2q minus 5. There you go. That's part A.
Why do you plug in 1?
Yeah,
Oh my
shouldn't it be
god,
two?
why did I do 1? You're right. That's crazy. It's supposed to be 2. I was thinking of the previous problem that we did on the homework. You were 100% correct. Thank you for catching me in that mistake. That was so stupid. I would have caught myself, hopefully, down the road. Oh my goodness. Can't believe I did that. Thank you for catching me. So it should be 2p plus 2. No, squared. It should be 4p plus 2. It's almost going to make another mistake there. Oh goodness. This is why you need a break. There's a minus there also. Okay. Px squared plus x. Qx minus 5. Plug in 2. 4p plus 2. Okay, good. 2q minus 5. Okay, now I feel a little better now. If I made a mistake, let me know. Okay, part B. Now assuming it's continuous, which we have. Complete the following for f prime of x, blah, blah, blah. So in this case, definitely use a shortcut rule. And I'll probably just tell you, just use a shortcut rule. So that's just going to be 2px plus 1. And that's going to be just q, because you have qx minus 5. Root of negative 5 is 0. Root of qx is just q. So you're left, and this basically means a left-hand derivative. Because what you're doing is you're approaching 2 from the left of a derivative. So that's going to be a left-hand derivative. Approaching 2 from the right of a derivative, that's a right-hand derivative. And at x equals 2, that's specifically going to be 4p plus 1. Because I plug in 2 for x right there, help me get that. And that's just going to be just plain old q. So if I want to be differentiable, at x equals 2, of course, it's just 4p plus 1 equals q. Now, I have two equations. I have this, and I have this. And I trust you guys can solve that just fine in part D, just using your system of equation knowledge. And that way your forces to be continuous and differentiable. I think the reason why we designed the question, and actually this question came from when I last taught this class, I think 2 or 3 years ago, and then Ms. Blanford, I think, recycled it but changed the numbers around for last year. We wanted to kind of guide you through the process. So this problem is very, very similar to that right there. Very, very similar. Just it's written a little differently just because we want to kind of guide you through the process of doing that. Oh, part D, sure. I'll go over part D. So you do substitution. I don't want to move the screen right now, but 4p plus 2 equals 2 4p plus 1 minus 5. So this right here is my first equation. I'm just doing substitution, right? Clean it up, you get 4p plus 2 equals 8p plus 2 minus 5. So you get 4p plus 2 equals 8p minus 3. Move things around, you should get 5 on the left, 4p on the other side. P is 5/4. If p is 5/4, then you have 4 times 5/4 plus 1 equals q. That's going to be 6. That's how you get those answers. I probably would maybe put this as a multiple choice question, but I have to see your work, you know, so. But yeah, I expect this question on our test tomorrow for sure. I do have another meeting coming up in about 9 minutes. So there are other questions that you guys want to ask about before we end the call? Let me see what else is going on here. Drawing derivative graphs, we talked about that. Remember, A and B and C have horizontal tangents. So you want to make sure your derivative graph is crossing the x-axis at -2, 0, and 3, which actually it doesn't do for D or C. And then, of course, the derivative is negative until you get to -2. So you want it to be below the x-axis. So the answer is going to be B for 8. 7 is kind of the same thing. 6 we talked about. 5 is kind of conceptual. 4 is kind of knowing how to recognize limit definitions of a derivative. 3 is, again, kind of conceptual, and of course plug in, find left right hand limits, left right hand derivatives, working that out. 1 and 2 are kind of cool questions, but let's see what is in the chat. Number 2 from last year's test. I'll do that right now. That one actually Ms. York designed about 3 years ago. So I was really excited when she created that one. That's a really good one. Really makes you think hard about it. We'll do that in just a sec. Yeah, and if you turn any homeworks, I should have updated. I should have updated homeworks in the discussions. So if anything I haven't quite updated, let me know and I'll take care of it. So thank you for anyone's brought that to my attention. Okay, so number 2. You want h prime of 4. Well, what's h prime of x? Think of this as u and think of this as v. It's going to be f prime of x times g of x plus f of x times g prime of x. Now plug 4 in. So by the way, you haven't seen a problem like this. And I could ask a question like 1 or 2 like that, like something you haven't quite seen. But conceptually, you know about product rule, right? You practiced it, so you got to apply it. So it's, just requiring some higher order critical thinking. We are an AP class after all. Now, G of 4 is easy. So basically, I got to find 4 different numbers here. I got to find F prime 4. I got to find G of 4. I got to find F of 4. I got to find G prime 4. G of 4 is easy. G of X is right here. G of 4 is just 1. F4 is also easy. That's just 2. Then these here are just slopes. So the slope of F looks like is 1. The slope of G looks like it's 3. No, 3/2. Gosh, that's a tricky one. Up 3 over 2, so that's 3/2. So you get 1 plus 3, the answer is 4. That's why it's D for number 2. But yeah, that's all you have to do for that one. It's just really conceptually, just know what a slope is, what a derivative is, the slope of a tangent line, know your product rule. That's a really good question. Number 1, just so you know, derivative pi is 0, right? And you just find first, second derivatives. That should be pretty straightforward, I think. See if we got anything else here. Might be worthwhile to talk about. For number 4, you just gotta be careful here. Remember, you're gonna do this definition when h is approaching 0, right? Not when h is approaching a. So that's why e definitely is a derivative. You have to have minus, not plus, so I is out, and so of course a is out. If you do the alternative definition, that's when x approaches a, not when h approaches 0. So c works. There's got to be minus, so b is out. It's not when a is approaching, it's when h is approaching 0. It's got to be a limit, so these are out. So just c and e. That's that one there. So the question is asking, do you want to write out the basic form of the rules before starting the problems? Like for, like, say, a product rule, product rule is this, right? No, not really. You don't have to. I mean, it's good to do to get partial credit. Wouldn't hurt. You don't have to. Or like, for quotient rule, u prime v minus u v prime over v squared. Again, it's up to you. I don't really care whether you show that or not, but if you do, it helps for partial credit if you happen to miss a problem. Okay, well, I'll need to end this call because I do have, first of all, I want to get the recording going so I can upload it to Schoology later this afternoon. And I also have another meeting starting in about a couple minutes I need to quickly prepare for. So I'm gonna stop sharing my screen. I'll end the call. If you want to come by during tomorrow's office hours, I am available at 8:15 a.m. So you have that opportunity as well. If you want to shoot me any questions, feel free to email me. I probably won't get to it till late tonight, probably not till after 9 o'clock tonight, but you can if you like. And I think that is it. Yeah, okay, great, cool. Well, good luck with your preparation, and I'll see you guys in class. And we'll start the test pretty much right away because we do have some students with 50% extended time. I want to make sure they get that during the class period. If you have double time, I did shoot you an email and sent you an invite to take care of that. But for anyone else who've recommended time or 50% extended time, you'll do it during class, and we'll start right during the normal class time. And of course, if you finish early, then you're done with class. So, okay.
Thank you, Mr. Reed.
See you guys.
Thank you.
Have a great rest of the
Hey,
day.
Mr. Reed.
Yep.
Thank you.
Welcome.